guys, welcome back. So I'm going to take you through the assignment, the thermodynamics assignment, the homework one. Okay, so let's start with question one. So the question says that at what absolute temperature do the Celsius and Fahrenheit temperature scale give the same numerical value? What is their value? So from this question, they are saying that the temperature from the Celsius scale, at what value is the temperature from the Celsius scale equal to what the temperature from the Fahrenheit scale. So what we deduct from this one is that see the temperature from what the Celsius, the Fahrenheit must be equal to what the temperature from what the Celsius. F is for Fahrenheit and C is for Celsius. And then the only equation that relates Fahrenheit and what Celsius is what temperature of Fahrenheit is equal to 1.8 temperature of what Celsius plus what 32. So from there, when you substitute in place of temperature in Fahrenheit for temperature in what degrees Celsius, you have temperature in degrees Celsius to be equal to 1.8 temperature in what degrees Celsius plus what 32. And when you send this one to the other side, and when you solve, you get the temperature to be equal to what negative what 40. Okay, so that's the value. They said the value, not so do not add degrees Celsius or Fahrenheit to it. It's just the value that they want, the numerical value. So the numerical value is what negative 40. Okay, so that's the first question. So let's move to question 2. So question 2 says the reading on a Mercury manometer at 25 degrees Celsius open to the atmosphere at one end is 56.38 centimeters. The local acceleration due to gravity is 9.832 meters per second squared. Atmospheric pressure is 101.78 kilopascal. What is the absolute pressure in kilopascal being measured? Density of mercury at 25 degrees Celsius is 13.534 gram per cm cube. So the things that we can get from this question is that, so say we should prepare some this parameter whatever. So we know the height is equal to 56.38 centimeters. We know gravity, we know pressure, atmospheric pressure to be equal to this, and we know density of mercury, which is rho m, to be equal to 13.534 gram per cm cube. So the first thing we want to do is to convert all the units here into their SI base units. Okay, so we know that the unit for height is meter, not centimeter. The unit for density, the SI unit for density is kilogram per meter squared, not gram per centimeter squared. So you have to convert all those things to their SI units. So that's what I did over here. The height is equal to this. And we know centimeter is 10 raised to the power minus 2. So when you convert this, you get 0.5638 meters. And then the density to when you convert it, you should get what? The answer, which is here, 13,534 kilogram per meter cube. Okay, and we know that atmospheric absolute pressure is equal to what? Gauge pressure plus what? Atmospheric pressure. Okay, absolute pressure is equal to gauge pressure plus what? Atmospheric pressure. And we know that gauge pressure is equal to rho what? GH. Rho GH. Rho is density, G is acceleration due to gravity, and H is the height. So when you multiply, we know the density of mercury is 13,534 times the acceleration due to gravity, which was given to be 9.832 times 0.5638. That's the height. When you solve this, you should get what? 75.02277 kilopascal. Okay, so that's the gauge pressure, 75 point something kilopascal. So now the absolute pressure, the absolute pressure will be equal to what? The gauge pressure, which is 75.02277 kilopascal, plus the atmospheric pressure, which is 101.78 kilopascal. So your final answer is what? 176.803 kilopascal. You double underline it and we are done. Okay, so that's what has been asked. So we have that. Now let's move to the next part, which is question 3. So let me read. A gas is confined in a 0.47 meter diameter cylinder by a piston on which rests a weight. The mass of the piston and the weight together is 150 kilogram. The local acceleration due to gravity is 9.8 0.13 meters per second squared, and atmospheric pressure is 101.57 kilopascal. So that's what we have. So the summary of the question, the preamble for this question is the diagram I've drawn. We have a gas in a cylinder, which is closed by what? A piston. That's the piston, this side. This is the piston. And there is a weight resting on the piston. So that's what I tried to write. And they said the mass of the piston and this weight together is what? 150 kilograms. So we know the diameter of this cylinder is what? 0.47 meters. The mass of the piston and the weight is 150 kilograms. Acceleration due to gravity is this. Atmospheric pressure is this. And then along the line, they've given us some height, which is 0.83 meters. Okay, so let's get back to the main questions. So the first question, they said, what is the force in newtons exerted on the gas by the atmosphere, the piston, and the weight, assuming the friction between the piston and the cylinder, assuming there's no friction between the piston and the cylinder. Okay, so the force exerted on the gas by this will be equal to what? The force exerted by the atmosphere. The force exerted on the gas will be equal to the force exerted by the atmosphere plus the force exerted by the piston plus the force exerted by the what? The weight. So in total, we'll be having 3 forces. So, and the force exerted by the piston and the weight will be equal to what? Mass times acceleration. That's equal to the weight that will be exerted on the gas. That's the 150 times the acceleration due to gravity. That will be the force exerted on the gas by the piston and the weight together. Okay, now let's calculate the force that the atmosphere will be exerting on the gas. So we know that pressure is equal to what? Force over area. So from there we can find the force exerted by the atmosphere to be equal to what? The atmospheric pressure times what? The area. And we know area is equal to what? Pi d squared over 4. So when you solve that, you should get 0.17349 meters squared. Okay, so when you input that, you should get the force exerted should be equal to what? Pressure, atmospheric pressure times area plus the mass of what? The piston and the weight multiplied by g. So when you solve that, you should get what? 19,093.3293 newtons. Please do not convert it to kilonewton, okay? So that it will be like 19.073 kilonewton. No, it's wrong. They said the answer should be in newton, so it should be in newton. Then let's look at the next question. The next question says, what is the pressure of the gas in kilopascal? Okay, the pressure of the gas will be equal to the force exerted on the gas divided by what? Area. And we know that the force exerted on the gas is equal to 19,093.3293 newton, or divided by the area of the cylinder, which is equal to 0.17349 meters squared. So when you solve that, you should get 110,054.35 pascal. So they say we should convert it to kilopascal. So converting it to kilopascal will give you 110.054 kilopascal. Okay, yeah, so that's that. Let's move to question C. They said if the gas in the cylinder is heated, it expands, pushing the piston and the weight upwards. If the piston and the weights are raised 0.83 meters, what is the work done by the gas in kilojoule? Okay, so let's start with that one first. Okay, the work done by the gas will be equal to the force exerted on the gas by the distance that the force that the gas exerts on the piston multiplied by the distance that the piston and the weight move. So that force is equal to 19,093 point this one times the distance, which is 0.83 meters. So when you should get 15,847 points. Yeah. Then you convert it to kilonewton, you should get 15.85 joules, not newton. So kilojoules. Okay, that's work done is in joules. Okay. Now the next part of the question says, what is the change in potential energy of the piston and the weight? The change in potential energy is equal to what? mgh, or is supposed to be mg into bracket h2 minus what? h1. But we know that h1 is what? 0. When you are drawing that one, the h1 will be 0, and then the final height that's which is the 0.83 meters. So the change in potential energy of the piston and the weight will be equal to the mass of the piston and the weight, which is 150, multiplied by acceleration due to gravity 9.813 times the distance moved, or the height, which is 0.83. 0.83, then this should give you what? 1221.7. Yeah, this was in joules. Then you convert it to what? Kilojoule. Okay, this should give you this answer. Okay, now let's move to the question 4, the last question, the question 4. So let me read. 1 mole of a gas in a closed system undergoes a 4-step thermodynamic cycle. Using the table above, find the missing quantities. Okay, so that's so you're supposed to study this table and then find some things. So I've summarized everything over here. So the process starts from 1, goes to 2, from 2 it goes to 3, from 3 to 4, then from 4 it starts like it's come back to 1 and ends at 1. Okay, so yeah, and ends at 1. So let's see. So we are going to be applying the first law of what? Thermodynamics to solve this question. And the first law of thermodynamics states that what does it even state? Okay, so the internal energy of a system can only be changed by 2 things. That is what? By adding heat or by doing work on the system. So that's how the internal energy can be changed. So the change in internal energy is equal to what? Q, which is heat, plus what? W, which is what? Work done. So that's the first law of thermodynamics. So we are going to be considering these steps one by one. And then from the study, you can see that some of the steps have like 2 values that you can easily find the third one. So we are going to be solving those ones first before we are going to focus on the ones that have the 2 missing, yeah, that kind of one. So let's continue. So from you are taking first step 1 to 2. Okay, so the change in internal energy from step 1 to 2 will be equal to the heat of the step 1 to 2, the heat applied in step 1 to 2, plus the work done in step 1 to 2. So that's the change in internal energy, which is given in the table to be equal to negative 200 joules, will be equal to the heat plus negative 6,000 joules. So when you solve, the heat from step 1 to 2 will be equal to what? 5,800 joules. So that's the heat that we'll get for step 1 to 2. And when you look closely, you can see that the other step that has 2 values that we can find, the third one, is step 3 to 4. So you are going to consider step 3 to 4. And in step 3 to 4, you write the equation from the first law of thermodynamics. The change in internal energy from step 3 to 4 will be equal to the heat applied in step 3 to 4 plus the work done between step 3 to 4. So we don't know the change in internal energy, but we know the heat applied, which is negative 800 joules, plus the work done, which is 300 joules. So from there we can find the change in internal energy within that step, which is equal to negative 500 joules. And then this is one of the important parts that you must consider. If you don't understand this, it means you cannot continue from here. Okay, so since the change in internal energy is a state function, then the sum, when you are doing the work, let me kind of go back to where that is. Okay, so because the change in internal energy is a state function, the change in internal energy between this process, from this process to this process, from process 1 to process 2, plus the change in internal energy from process 2 to process 3, plus the change in internal energy from process 3 to process 4, must be equal to the negative, because the work is going back from 4 to 1. So it should be equal to the negative of the change in internal energy from 4 to sorry, from 4 to 1. Okay, so when you add the change in internal energy from this to this, plus from this to that, plus from this to this, should be equal to the negative from 4 to 1, because we are going backwards. So when you do that, you get that the change in internal energy, you get that the change in internal energy from 1 to 2, plus the change in internal energy from 2 to 3, plus change in internal energy from 3 to 4 should be equal to the change in internal energy from 4 to 1. Okay, from 4 to 1, the negative from 4 to 1. So when you solve this, you should get the change in internal energy from 2 to 3, which we don't know from the table, to be equal to negative 4,000 joules. Okay, should be equal to negative 4,000 joules. Then since we know the change in internal energy in the process from 2 to 3, we can now consider the process from the step 2 to 3 to find the work done in step 2 to 3. So then you write the equation from the first law of thermodynamics. The change in internal energy from 2 to 3 is equal to the heat applied from 2 to 3 plus the work done from 2 to 3. So this will be equal to negative 200 joules. Okay, now there is another concept to also apply. So at the bottom, we are given the total work done from step 1 to 2 to 3 to 4 to 1 again. We are giving the total work done to be equal to what? Negative 1400 joules. But we know that the total work done in the whole process will be equal to the work done at each step. Will be equal to the work done at each step. So the total work done from 1, 2, 3, 4, 1 should be equal to the work done between step 1 to 2 plus the work done between step what? 2 to 3 plus the work done between step what? 3 to 4 plus the work done between step what? 4 to 1. You add all of them, that should be equal to the total work done. You consider the steps. So we have negative what? 1400 should be equal to negative 6000 plus negative 200 plus 300 plus the work done from what? 1 to 4, which we don't know. So you from here you can be able to find the work done from 1 to 4, which will be equal to what? 4500 joules. Okay, 4500 joules. So after finding this, then you consider what? The step what? 4 to 1. Okay, so now let's consider the step 4 to 1. So you write from first law of thermodynamics, changing what? I'm coming this about. Okay, so from step 4 to 1, the change in internal energy from 4 to 1 is equal to the heat applied between from 4 to 1 plus the work done from 4 to 1. Okay, so we now know that what? The change in internal energy from 4 to 1, which is given to us to be what? 4700 joules, to be equal to the heat applied from 4 to 1, which is what? Which we don't know, plus what? The work done between 4 to 1, which is what? 4500. So when you solve, you get the work, the heat applied between 4 to 1 to be equal to what? 200 what? Joules. Okay, so now let's look at, now we are done with that one. So now let's look at the last part of the question. Now we know that since change in internal energy is a state function, it means that all the change in internal energies, the total change in internal energy within the process from step 1 to what? Step 4 should be equal to what? 0. Okay, so we can prove that by adding all the change in internal energy. So the total change in internal energy, which is equal to change in internal energy from 1 to what? Like 1, 2, 3, 4 up to 1 should be equal to what? The sum of all the change in internal energies. Okay, so the change in internal energy from 1 to 2, the change in energy from 2 to 3, the change in energy from what? 3 to 4, and the change in energy from what? 4 to 1. And all this, if you sum, it should be equal to what? 0. So when you write the equation from the first law of thermodynamics, you get that the total change in internal energy will be equal to what? The total what? Heat applied plus what? The total work done. So from here you get that the total heat applied, which we don't know, is equal to what? Negative of what? The total work done. And we have been given the total work done to be equal to negative what? 1400 joules. So from here you get what? Your total heat, which is applied from step 1, 2, 3, 4 and back to 1, should be equal to what? 1400 joules. And this is the end of this question or this homework. I hope you understand. If you don't understand, please, you can reach out and ask questions. Please don't forget to subscribe to our new channel. Very soon we want to hit 10,000. Okay, subscribe and tell your friends to subscribe as well.